All right, so we only have 3 more sections left. All right, we're finishing with chapter 5 for this year. We have 5.5, 5.6, and 5.7 to do. Most of 5.5 is a review of derivatives and integrals that you've learned in the past, and then something a little new. So basically here, we're looking at bases other than e. So like instead of having like e to the x, maybe we're looking at 5 to the x or 2 to the x. So I summarize this by going over the different types of powers that we know. So one is a variable to a constant. So an example would be like x to the fifth, 2x minus 7 to the third, x plus 2 to the negative 1/3. Those are powers where your variable is the base and you're raising it to a constant. How do we derive these? You take the power, bring it in front, leave the inside the same, subtract 1 to get the new power times the derivative of the inside. That's chain rule. How do we integrate these? Well, as long as n doesn't equal -1, you add 1 to the power, divide by the new power. If n does equal -1, meaning it's du over u, or u to the negative first, it becomes the natural log function. So this is just all a review of stuff we've done. Next, if we have a variable or a constant to a variable, so the base is a constant and you raise it to a variable power. So e to the 5x, 3 to the x, e to the sine x, 5 to the tangent x. A is considered a constant. So when we derive e to the u, it's e to the u times the derivative of the power. We learned that earlier in this chapter. When we integrate e to the u du, it becomes e to the u plus c. Now, that is a review. What's new is if you have a to the u, a is a constant other than e. So a is any number, okay, other than e. So when you derive these, you keep it the same, you times it by the natural log of the base, and then you times it by the derivative of the exponent. When you integrate these, it becomes the same thing divided by the natural log of the base. So let's practice deriving a couple of these. So here, okay? So to take the derivative, this is the a to the u formula. So you keep it the same times the natural log of the base, which would be the natural log of 2, times the derivative of the exponent, so it would be times 1, because the exponent is just x. So your answer here would be 2 to the x times the natural log of 2. There you go. All right, the next one, 5 to the sine x. Okay, so this is the a to the u formula where a is 5. So you keep it the same times the natural log of the base, so the natural log of 5, times the derivative of the exponent. The derivative of the exponent would be the derivative of sine, which is cosine. Oh, I don't know what happened there. That's supposed to be part equals. So 5 to the sine x times the natural log of 5 times cosine x. There's your answer. All right, so the next one, all right, this is the a to u formula because your base is a constant other than e, 3 in this case. Sorry, I keep adjusting here. So you keep it the same, so 3 to the 5x times the natural log of the base, natural log of the base, times the derivative of the exponent. The derivative of the exponent is 5. So I'm fine if you leave that as your answer. All right, and when you take the derivative of e to the u, you keep it the same. Times the derivative, right? We're following this formula right here. Times the derivative of the power. So the derivative of cosecant is negative cosecant cotangent times the derivative of the inside. Derivative of the inside is times 2. So we use the little chain rule there. So You do want to clean this up a little bit. I would make this -8, right? 2 times negative times 4, -8. Probably looks best to bring it out in front. E to the 4 cosecant 2x times cosecant 2x cotangent 2x. There we go. All right, with integration, when you have an exponential function, whether it's base e or base other than e, try to make u the power and see if that works. Now, you know if it works, if you take the derivative, you should get your du in the problem already, except for maybe a constant. So you already have, look, you already have the x dx in there, so we need to put a 2 in and multiply by a half on the outside. And you end up getting e to the u du. Okay, and that integrates to e to the u, which I'll plug u back in, plus c. All right, so when you have an exponential function, try to make u the power. So looking at this, the exponential function is 2 to the cosine x. So try to make u cosine. The derivative of cosine is negative sine. You know you're on the right track because the sine's in there. Just a negative on the outside. This ends up being 2 to the u, and the rest of it is my du. Now, what we're doing is we're following this formula right here. In this case, our a is 2. So this integrates to negative, because that negative is on the outside, 2 to the u, so 2 to the cosine x, divided by, I'm literally just following this, guys, the natural log of the base, so the natural log of 2 plus c. There we go. All right, and the last integration problem here, if you make u, what do you think you want to make u? All right, the power, 4 minus x to the third. All right, now we have to very carefully derive this. So we have to use what rule to derive this? Chain rule. So bring the 3 in front, leave the inside the same, raise it to the second power, times by the derivative of the inside. People are going to forget that times by -1. Now, times dx. So this, look, this is basically in there right here, except for the -3. So I put a -3 in, and that means on the outside is -1/3. So -1/3, the integral of 3 to the u du. And now what we're doing is we're following this formula up here. So it's -1/3, 3 to the u, so I'm going to plug my u back in, divided by the natural log of the base, so the natural log of 3, and then plus c. All right, so now you've seen two different types of powers, a variable to a constant to a variable when the base is e versus the base is a number, something other than e, how to integrate and how to differentiate those. And the last but not least is a variable to a variable. So a variable to a variable is a variable base to a variable power. Lucky for you, you only know how to derive these. And the way to derive these is to use logarithmic differentiation. What that means is you go right into taking the natural log of both sides. So you take the natural log of both sides, and then you expand the right-hand side. So to expand the right-hand side, this sine x, remember any exponent of a natural log can be expanded to the front. And now you want to take the derivative of both sides. So derivative of ln y, so derivative of the inside, so derivative of y is dy over dx over the inside, equals, to derive this, I have to use what rule? Product rule. So first times the derivative of the second, the derivative ln of x is derivative of the inside over the inside, so it's 1 over x, plus the second times the derivative of the first, the derivative of sine is cosine. Now the very last step is to solve for dy over dx. So what you end up doing is, and I'm going to write over here because we're not going to do example 9, is you end up multiplying through by y. Multiply that y over, so I get sine x over x. When I simplify this, sine x times 1 over x is sine x over x, plus the natural log of x times cosine of x. And then, I don't know if you remember from before, the last step is always to show that you know you're supposed to plug y back in. And I said, I don't mind if you're lazy, if you just circle what y is equal to and you substitute back in. And then that's your final answer. So when you have a variable to a variable, the only way to derive these is taking the natural log of both sides.